Hi, I'm Guang, 15 years old. In this lesson on the methods of definite integration, we will continue taking a look at the example we had from the previous lesson. Right, so this example here, we're supposed to evaluate the line integration along a certain curve, and inside you have y cubed dx minus x cubed dy, where C are the two circles of radius 2 and 1, and that these two circles are concentric, so they're both centered at the origin with positive orientation. So once again, you need to be able to understand what this question exactly means. So first of all, you have to be aware this is, after all, a line integration. So line integration, it will be kind of different from your normal kinds of integration, which later on you'll see how you can change them into normal integrations and all. Well, that is the first thing. You need to know what kind of question you're dealing with. Now, the second one is on what kind of boundary you're seeing. In this case, you have two circles which is making a ring shape, pretty much a donut shape, more like, alright? So, for this case, since you also need to look at the question and realize it is in positive orientation. Now, what does it mean by positive orientation? So, a way that you can think of this, if let's say you're taking a look at this donut shape, it will be, let's say you're running along the sides of it, running along the circle. So what will be so special when it is a positive orientation? That means, let's say if you're running along it, then the entire area, or not exactly entire sometimes, but whatever is close to you, it has to be on the left side. So let's say you're on the outer ring, so then you have to be running anti-clockwise, since it needs to be on your left side. Alright, so that is pretty much what it means by this positive orientation. Now, what happened before was, we changed all of this line integration into multiple integrations. Well, if you wanted to see how exactly we did it, you can go back to the previous lesson to watch it again. Alright, so what's so special about that? That method, what you had to do was actually to kind of cut it through the center and split it into multiple pieces so that you can work with the outer ring into the inner ring in one smooth path. Alright, so that is pretty much what we did for the last lesson. But if you really want to know how the calculations work, again, you can just go back to those lessons. But then what would be so special for this time? So since last lesson, we changed them into separate integrations one by one, how about we take a look at something different this lesson? Well, instead, we'll just be directly applying the green theorem. Which, the green theorem, we have covered it a few times, and if you can recall it, it is essentially this formula over here, where maybe your teachers might have just asked you to remember this entire formula, so that next time when you need to use it, you just know that that certain line integration means it can be written as this double integration. But what's exactly so special about this? So the line integration, p dx plus q dy, assuming p and q are essentially functions of x and y, and then this part on the left hand side will be equal to your double integration on the right hand side, where if you take a look at this, you have partial q, partial x. So you would also have to be aware of the change of whatever in front of your x and y, alright? So when it is in double integration, it will be partial q, partial x minus partial p, partial y. So this part you have to be aware, and of course finally whatever you like to use it. Some people prefer the sigma, some prefer dA, some prefer to just write it as dx dy. Alright, but that doesn't exactly matter here right now. So what will be so special for this part? Now, one thing you might realize is that it is partial. Well, partial because p and q, they are essentially both functions of x and of y. Although, just because they're both functions of x and of y doesn't mean you can't have this type of question where In this case, if you look at your p, it is only a function of y. And if you look at your q, it is only a function of x. If it's a function of both, well, it can be pretty much about anything. Alright, so that's pretty much it about this Green's theorem we currently have over here. So how about let's take a look at how we use it in this example here. So of course, first of all, you see it here. You have this line integration along your curve, and it is y cubed dx, and then you have to subtract x cubed dy. So you would want to write it in this form, isn't it? So after all, you would have to once again determine your boundaries and everything, isn't it? So what will one possible problem you face be? So of course, you can still, let's say, define this as over your entire area or D domain, whatever you like. So over this entire area, now you go straight into your differentiation. So what will be so special about this differentiation over here? I will just write the double integration closer. So inside this double integration, you have partial q, partial x. So what is your q in this question? So since q is in front of dy, so q is negative x cubed. So you have to be aware that there is a negative in this case. So you have negative 3x squared. Or if you want to write out the entire thing, then there will be a partial negative x cubed partial x, which, well, if you can see it, that is a negative 3x squared. Then next, you need to subtract partial p, partial y. So what's our p here? P, we take a look at the question again, that will be y cubed. So y cubed, you differentiate it with respect to y, which in this case is just 3y squared. And then you have dx dy. So now that you have gotten this form, what is the next problem that you might think of? Well, of course, how do I determine what my boundary is? So this is in your Cartesian coordinates, and in fact, in a double integral Cartesian coordinates form. Now, to change it into iterated, is there any way to make it simpler that you don't have to use much other functions just to represent your boundaries? So of course, if you have learned it before, you could change it into polar coordinates, since if you realize this is a circle, and for a circle, most likely you'll be thinking of polar coordinates. So how do we change this into polar coordinates now? So two things, you have an r, you have a theta. So r will be from your inner circle, which is radius of 1, to the outer circle, which is a radius of 2. And then of course you have your theta, but in this case you have to be pretty aware of what the theta will have to be. So theta, what will happen is that you'll have from 0 to 2 pi. Alright, so this is what you'll see. Next, negative 3x squared minus 3y squared. What's so special about that again? Now, in polar coordinates, r and theta. So to change Cartesian coordinates into polar coordinates, x is equal to r cosine theta, while y is equal to r sine theta. Now, using your basic trigonometric functions, identities, you realize x squared plus y squared is equal to r squared. So what happens here becomes negative 3r squared. Alright, so that is if you can see it very directly. Otherwise, you might want to factorize your negative 3 first in order to see your x squared plus y squared. Or if you really can't see it, then change x into r cosine theta, y into r sine theta. Alright, so that is for the integrand of this double integration. Now, what happens to the other part, which is your dx dy? So, dx dy, it will become r dr d theta. Alright, so r dr d theta. Now, what you see here is essentially what you could change into a simple iterated integration. Integrate from 0 to 2 pi d theta. And then on the outside you can have negative 3, and of course integrate from 1 to 2 r cubed dr. Alright, so what you have here? So negative 3 stays on the outside. Then integrate from 0 to 2 pi d theta, which you essentially have 2 pi minus 0, or theta substitute 0 and 2 pi, whatever you like to write it as. So this part here becomes 2 pi. Now what happens to this part? So once again, your basic integration formula, r cubed, you have a 1 over 4, and then r to the power of 4, substitute in 1 and 2. So r to the power of 4, which means it is 2 to the power of 4 minus 1 to the power of 4, which is 16 minus 1, which, if you could find it early, that would be a 15. And thus, you have a negative 45 pi over 2. Alright, so since you have 15 times 3 times 2 divided by 4, and you get the final answer of negative 45 pi over 2, which, if you go back to our previous lesson, they are consistent, which means both of these methods are right. It's just that one's more complicated, but pretty much easier to understand. And the other method here is directly applying your formula, which of course, once again, you have to be aware of various things, its signs, and what functions you have to differentiate, which functions you have to differentiate it with respect to what and all, alright? So then of course, in this question, there's a trick of using your polar coordinates. Since Cartesian coordinates, it could be rather more complicated, but of course you can still try, which since there's all your circle functions and all. But this is pretty much it for this lesson. Well, we once again covered what this entire question means, and of course showing this can be an application of your Green's theorem. So I hope for this lesson you're clear of everything so far. So using a Green's theorem, one complicated question like last lesson can be solved this quickly and simply. And I hope you enjoyed whatever's being taught here just now, and thank you for your watching.